So good morning guys, today we're going to be looking at our little custom primary flight display. It can mount on a Honeycomb Bravo yoke. I'm guessing it can mount on a Logitech yoke as well, and you can just put it on your desk. You can do whatever you want with it. Mine is pretty firm on here. Let's see, we have some double rotary encoders going on. There we go. Got touch screen capabilities, like I can swap the frequencies with a press of the screen. I wanted to say button, but is it a button? If you press something on the touch screen, doesn't matter, it works. We can control the ATC from here. Let's say command 1 is going to do something. I need to open the ATC menu to actually see if something's happening. Request flight following, here we go, 1. Perfect, wonderful. So we got that going. We're going to be adding more screens like the GPS, we're going to be adding the fuel information and many more over time, but we're going to do it in a bite-sized chunk. Nobody wants to watch a 2-hour documentary on how to make this thing. So this week we're going to be looking at how we can wire this up, what components we need, what kind of board we need, because let me tell you a secret, we're not going to be using an Arduino for this one because an Arduino just simply can't keep up. Well, because we want a PFD that's affordable, we went with a quite low-cost LCD screen. What is the downside of it? Well, as you might be able to tell, filming it can be quite hard. So the colors that you guys see aren't the colors that I see, and that's A, because an LCD screen is quite a cheap one, and B, I don't have the most advanced camera out there. Now this project can really be customized to your complete liking. You can use your own colors, your own graphics, your own interfaces. I'm just going to show you the basics, how you can do things, give you some tips, give you some examples. Now we're going to start out with the comm screen. Later on, we're going to add the fuel gauges. We're going to add some basic GPS functionalities. Nothing as fancy with a map like a G530 or anything, but just a graphical overview from your heading to the next heading, etc. So if you think there is something that I'm missing that you need on something like this, let me know, and perhaps we'll edit it in a later video. Now, if you can't follow along with the video, don't worry. I will also put a link to a written article that explains all the wiring diagrams and everything that I tried to explain in this video. So if you like it, leave a like, and if you want to keep updated with the rest of the series, don't forget to subscribe. Let's just dive right in. My main goal was to keep it modular, serviceable, and create a way that we can mount it on other hardware or just put it on your desk to your liking. So right now, you might be able to tell that it doesn't have a bottom on it. I've created a base that really clicks onto the PFD screen and keeps it firmly in place. Let's see if we can. It's actually quite a tight fit. Here we go. And it's quite secure. Only if we apply some force and pull it upwards, the PFD screen gets removed. But it's quite, you can just take it off whenever we want to, without too much of a hassle, and it keeps on there pretty well. Now, another plus of this is that we can access all of the components in the back, and I'm going to show you how. Now, for the first time, I've tried to use connectors for almost any component that I've mounted in here. So here we can see that we've got the screen. I very lazily glued in place because I couldn't be bothered to create something that really fit the screen and kept in place without too much of a hassle. But it's connected towards my microcontroller with a, and the same goes for the microcontroller itself. We can just take it. Let's first pull the cable out before we short something, shall we? Here we go. We can pull out the microcontroller. We can pull out the microcontroller without too much of a. You're gonna do it straight, not in an angle, or else you will bend the pins. But here we go. We can replace this one quite easily. Here we see that we have the 2 rows for the connectors, put it in, there we go. And everything is connected to those separately. Same goes for the rotary encoders, because I have a dual concentric one, and I don't believe it's a KY40, but an HW40. It's just basically the same, just a shorter shaft. And if I want to remove the rotary encoders, I can just resolder them to this proofing board, and the cables will be already in place. And we can just wire them up again like this. We just click them in, and we click them in. There we go. So So that's a really neat feature. For this, I picked up a new set of crimping tools. It comes with all these kinds of headers that you can mount towards the cable with these pliers. And then it's just a matter of plug and play. It even came with standard DuPont connectors as well. So you can create your own DuPont connectors of cables. Most of the microprocessors that we've used before were Arduinos. So we've got Arduino Leonardo, we've got Arduino Mega, Uno, Pro Micro, Nano, whatever. And they work fine for something like a toggle box. They're cheap, they're easy to implement, not big of a deal, but they aren't really that powerful. For a project like this, for a screen this size, we really need something beefier. Now there are several options out there. STM32, which is a bit more complex to start out with. So I wouldn't recommend really going that route immediately, but luckily we still have some cheap options that really knock some things out of the park, like the ESP32. They can be bought for something like $10 a piece separately if you buy them from something like Amazon or local retailer. But if you buy them in bulk, they're usually cheaper. I believe 3 of them comes down to $20. So it's a really cheap option and it's lightning fast compared to an Arduino. It has Wi-Fi capabilities, Bluetooth capabilities, everything that a real nerd can dream of in a small cheap package. If you really want to knock it out of the park, we also have an Teensy. This is a 4.1, really powerful capabilities beyond your dreams. The only downside is that these ones cost around $30, while these cost, well, like I said, between 7 and 10. So it's up to you. If you want the best of the best, go with a Teensy. You know, be wild, have fun. If you can miss the money and you're like, why not? If you're like, I want a more reasonable microcontroller, go with something like an ESP32. Now, when it comes to screens, there are also many options out there. The 4-inch screen is actually quite hard to source, I think. They can be obtained from AliExpress. Sometimes I can spot 1 or 2 on Amazon as well. Perhaps a local retailer has it. It's a very generic screen. It is a no-name brand, 4-inch SPI interface with touch capabilities. Now you also have these in Dino variants. These are more easily obtainable. The small one is 128 pixels by 160 pixels. Really handy if you want to display some small information chunks. You have some sizes in between, 3.5 inch, 3 inch to 2.8 inch. So go with whatever suits your needs. I'll put a link to the 4-inch one in the description. I think it's really the best size if you want to do something like a custom PFD. It will be something around 10 to 12 bucks. So it's a little bit more pricey than a normal toggle box that we're going to be creating, but you know, you can also just go with a casual I2C LCD screen if you just want to display textual data, and that's fine as well. So yeah, we won't be focusing on this one. We will mainly and purely be looking at this. So our screen makes use of the SPI protocol, which is Serial Peripheral Interface. SPI is a way that we can communicate with multiple components over the same data lines. So we have a full duplex way of communicating, which stands for data going out and in at the same time. If we only would have one data line, we couldn't be sending and receiving simultaneously. Things would just be a big mess. Now with SPI, we have a dedicated input and a dedicated output line. Now the terms that usually are corresponding with this is MOSI, MISO, CLK, and CS. MOSI stands for Master Out Slave In, MISO stands for Master In Slave Out, CLK stands for Clock, and CS for Chip Select. Now Master Out Slave In is the foundation of this principle, well, at least these terms. We have a master device, which is going to be the ESP32, and we have a slave component, which is going to be, in this case, our TFT screen and our touch controller. They are separate entities. MISO, master in, slave out, is going to be the data line that receives data from the component, so into the master, out from the slave. The CLK determines the rhythm at which this data transfer goes either left or right, doesn't matter, but it's just a set to determine at which base data comes in or leaves the device. Chip select is what makes all of the above possible. Because imagine if you would have your LCD screen connected, you would have your touch screen connected. Perhaps you have another SPI component that sends data like a crazy. How do you know which data comes from which device? They're all hooked up to the same MOSI, MISO and clock pin. Well, by having an own separate chip select line, pulling it high, we know that this component is active, so the data that comes in comes from this component. If you pull the touchscreen high instead of the screen, we know that the data that goes from or to this line is only going to the line that has the chip select active. So that's a really short principle basic how the SPI interface works. Now a lot of people will show you how to wire things up like this, but in my opinion you can't really tell what's going on and you don't get a clear overview, so we're gonna try to do it with a little animation. So you can't just hook up an ISP device to any pin on your board. There are several dedicated ISP pins on an ESP32, or Arduino has separate ones and TNZ has its own as well. So if you're not using an ESP32, please make sure that you check out the pinout from your board that you're using to ensure that you're using the proper SPI pins. They're usually marked MOSI, MISO, CLK, and the chip select can be any GPIO pin out there. On our LCD screen, we notice that there is a T_DIN pin, and there is an SDI pin, which is at the screen level. The 4 pins or 5 pins at the top are the touchscreen, and the rest below that are for the LCD screen. Now, SDI stands for screen data in, and T_DIN touch data in. Because we use the SPI interface, these can be connected to the same pin on our ESP32, which is going to be pin 23. So we also have a data out on a touchscreen. So master in, slave out. Because we don't want to retrieve any data from the LCD screen, in our instance we're only going to be using the T_delta Oscar, so data out. It's going to be connected to pin 19 on our ESP32. And like I mentioned, the CLK, so what's going to determine the rate at which the data flows, is going to be the SCK and the T_CLK at the top. Now both these pins can be connected to pin 18 of your ESP32, and you don't need to have separate lines, you can just combine them into one connection. And then last but not least, to determine which component currently receives or sends data, we're going to be using the CS and the T_CS, so chip select. And by pulling the signal high on either one of those, we know where the data is going to. Now, because these have to be separate, you can connect them to any GPIO pin you'd like. They don't have a dedicated one on the ESP32. I went with 15 and 21. The VCC and the LED line can both be powered by the 3.3 volts line that you're able to find on the ESP32, and the ground line goes to ground. The reset can be connected to pin 4, and the DC/RS can be connected to pin 2. Now these are just other things that the screen needs, like the power, ground, etc. The LED needs to be backlit and a way for it to reset the screen. Now a full diagram can be found in the article on my website, so don't be afraid if you didn't follow along or you missed where you need to connect which. Now we're going to also be working with a dual concentric rotary encoder. For this I bought a cheap one of €6 on AliExpress. Well, cheap is relative, but they are very cheap when you compare it to more known brands over the world with dual concentric rotary encoders. So $6 was quite a steal. The only downside is that they are a little bit more, well, they aren't complicated, but they require you to read the datasheet. Now, why do I say this? It's because it has 8 pins, and you can't really tell which pin does what, right? We have 3 on this side, we have 5 on this side, and what is up with these pins? How do they work? How do they need to be powered? Normally it's on a little breakout board, this one doesn't. So how can we determine what to do with it? Well, quite simple. If you go to the shop page, you can already see that we have an ACB, ACB, D, and E. Now D and E looks very similar to a switch to me, like open, close. So if we press down on the rotary encoder, it has a switch like most do. So we can quite deduct that the D and the E will be for the switch, and then the ACB, ACB will be for either the outer ring of the rotary encoder or the inner shaft. This also gets kind of confirmed down here when we see A signal off on, B signal off on, And we once again see switch, D and E. So we know now for quite certain that we have ABC for the rotary encoders and the D and E for the switch. Now, but how do we need to wire up this rotary encoder? Because usually it has little resistors on side of the breakout boards. Well, for this I did a quick Google search of just the product number or the name type, whatever, always quite technical. And the first link just gave me a reference sheet or data sheet that you can look into to see more info about the product, dimensions, and how you can wire it up. Now, this is the part that I was looking for. We have a sliding noise test circuit. Here we see that our part also is included in this range. So this applies to our part. We have our terminal A, terminal B, and terminal C, like we've seen on the AliExpress shop page. Terminal A and B require voltage with resistances, and terminal C goes to ground apparently. So this already tells us that the middle pin of the rotary encoder needs to be connected to ground on the inner shaft, the outer shaft, and because we have a button, we might as well connect it to ground as well to use it as an input pull-up. Now I gave away a little tip: input pull-up. Make sure that it pulls the signal high with a resistance to power a line. If contact is made, it's pulled low, and that's how we determine if a signal has changed. Here we also need to apply two resistances and a voltage. Now, luckily for us, if we use the input pull-up, this voltage will already be applied and the resistors are activated. So we don't need to create a special circuit or anything. This will work just fine. And if you take a look at the normal rotary encoders, they're usually marked with ground plus switch data and click or clock. Click, I believe. Doesn't really matter. But they are more clearly marked for you to easily spot where everything goes and where to wire things up. So these kind of speak for themselves, while these require a little bit more of reading. So I would suggest to start reading up on datasheets, because then the more you read them, the more they make sense and the more you understand basic circuitry. Now, if we want to wire up this rotary encoder, we have our 3 pins and 3 pins on either side and the 2 pins in the middle for the switch. So it's going to be our A, C, B, and ACB and D and E. If we want to use internal pull-up resistors for the switch, we have to make sure that one line is connected to ground and the other to any free GPIO pin. I've went with pin sync 26. If you want to follow along with the coding exactly like I did, and just make sure that it's connected to the same pins as here as well. These you can normally just freely choose which ones to use, because most pins on the ESP32 have interrupt capabilities. Now pin A and pin B both are connected to pin 23 and 33. Now for either the inner or the outer encoder, I've connected the A and B pin to pin 23 and 33 on our ESP32 respectively, and the same goes for the other side. Those go to pin 25 and pin 5. Now the grounds, you could wire up 3 wires separately to a ground line, but just solder them together, or but just make your life easy, solder them together into one connection. So from the outer pin towards the push button in the middle, towards the outer pin on the other side, directly to ground. That way you only have one cable running from the ground on the board towards the ground line on wherever you've mounted your dual concentric rotary encoder on, without having to have too many wires in there, less points of failure, easier to maintain. So now you don't have to solder anything for these projects. You could just use a breadboard, put a screen in there. The ESP32 usually comes with, the headers pins where they are sticky on the bottom. So you can't really put anything in it like here. Here you can just put in the cable. This one you can, however, mount on a breadboard. Just push it down, plug it in, and then wire the cables. Well, that way, just like, connect this one here. I don't know, something like that. But just to show the point that it can be done with a breadboard alone. It's just a little bit more of a work. Well, it depends on how you look at it. Make sure you have a wide enough one though, because I don't think, this will leave almost no room for your wires to fit on the sides. You need at least 2, or get creative. Now, the dual concentric rotary encoder unfortunately needs some soldering. They can't be put in directly into breadboards. The pins just won't fit, which is fine. I can't stress this enough, but soldering really isn't black magic. You can get a very decent kit for $40, 40 euros. Pick one up from, I don't know, your local reseller, Amazon. If you want a really fancy one, $100, 100 euro mark. And then you get a station like this. Yeah, it looks, we also have a black silverish color, but you know, this is the brand color. So I was like, why not? If you go all the way, you might as well go full on blue and yellow. I mean, so today we've kind of looked on how you can assemble a project like this, how you can wire up the screen, what kind of protocol it works, how to wire up the encoders, how you can look up the data sheets, very important. So get crafting, I would say. In the next video, we're going to be looking at how we can code up our first screen, how we can create the first graphics, and how we can display anything that you want to on a screen like this. So if you made it this far, thank you very much for watching. To keep things bearable, I would say start crafting, start tinkering around, you know, create something of your own, make something similar. And go check out the 3D files in the description down below. Written article and the 3D files were already out for my Patreons, so they could already start crafting before the launch of this video. So if you're interested in that as well, go check out the link in the description. For all my patrons, thank you very much for the support. Don't forget to leave a like, hit the subscribe button, and I hope to see you in the next one when we bring this monster to life.